Um, Today I'm going to work on the 4coder Lexer, and I was actually just looking at it a little bit for about 20 minutes before the stream started, just to refresh my memory again. I felt like last time I tried to do this, I couldn't remember how everything worked. So what I discovered is that the current thing that I'm working on is this keyword identifier thing. I said identifier because I saw it on screen, but it's not. The keyword parser thing. If this starts working, then I can eliminate the background buffer that buffers up the characters as they come in, which will speed up the central loop a lot. This part might be a little slower than it was before, but it might be just as fast. I'm not sure. I mean, it was already doing a hash, so it already had to go across the entire string again, make a hash, and then look it up and see if it was there. So, that's probably not great. What this is doing is arguably crazier because it's doing for each character, it's doing a lookup into a lookup table, and it does a few of those, and then it goes to another lookup table and does a few. I'm not sure. It seems like it could be, because each of those lookup tables, the first lookup will be cache cold, but the next ones will all be cache hot. So it seems like that could be just as good or bad as the hash table, really. The only thing that is definitely worse is that it takes up more memory, and that's one thing I want to optimize someday later. But for now, we just need to get it to work, right? And it's very close now. So what I was looking at is this this thing here, and I realized it's just ready, almost ready to work. I moved some things around, and I now have a system for computing which submachine is supposed to run. Because if I remember correctly, the way this works is that the whole this finite state machine works by saying we've got basically three types of states. We have machine local states, which are the lowest numbers. Then I should do this the other way around so that it goes left to right in the camera. So we have machine local states, right? And that's like your 0 through whatever. I think it's 26. And then you have, and the reason it's 26 is because 26 characters, right? It seems like a good number. So there's 26 states reserved for machine local behavior. Then there's a bunch of states that represent, if you're in this state, that means you want to transition to a new discrete state machine and then set your state back to 0 and run on that machine. And then there's terminal states that say, if I'm in this state, that's it, we're done, we have our result, and it's encoded in the result state. Right, so we have the numbers 0 through 255 are partitioned into those values, into those categories. And so when we come out of this internal loop, all I have to do is check the state and say, hey, look, if the state, there's a few reasons the loop could end. We might be at the end of this chunk and we need to get a new chunk, in which case we don't want to update which submachine we're looking at. But we might also have gotten one of those middle cases, states, that says we need to transition to a new state. So if that happens, what this code here, and I was just writing it, needs to do is first it finds out what the new submachine is going to be by just taking the state and subtracting out the first number so that reshifts everything, right? So the first table is at 26, which is what this should be defined as. So I just subtract that out and I get, okay, so that's 0 is the index for that. So in all the tables that are for like looking up the lookup table and the equivalence class table, if I put in a 0 there, I get that. Now what I should do, if I was smart, what I would do is I would, let me put in a to do here, rebase these super tables so that we don't have to do a subtract on the state, right? So the point is, this pointer here and this pointer here just encode some value that we're doing a plus on anyway. We're starting at that address and we're plussing something to it. And the amount we're plussing is this state minus this number. Well, if this minus is always going to be the same, what we could do is just build that into these pointers up here at the top, and then that minus will always apply, and we won't need to subtract stuff out of the submachine to begin with. The only thing we would then have to change is make sure that this is always equal to ls key table transition when we first initialize the submachine value. But then we could take out this subtract here, and it would all work without one less operation at runtime, right? So that's something I should do. But like I said, we're not quite ready to optimize stuff yet. It needs to work, and I think it's getting close. So let me just show you what the most recent bug is. Hey, is the audio worse than usual? I don't know if maybe James is just not used to how my stream audio is always a little weird. Is it worse than usual though? Because sometimes things go haywire and I can adjust stuff a little bit, but I've never been able to get that to stop, and I don't know where that comes from. I really don't. Like I tried just like, you know, I tried just like dealing with it by moving stuff around, plugging into different ports and stuff. It never helps. Um, I see a question from Bad Fly Dog, which I'll answer soon. I want to take a look at audio stuff real quick. Let's see. So this is the one we care about. Properties. Yeah, I don't know. I've never been able to figure out what's wrong with this. This is something I deal with from time to time. I can't turn that down at all because that becomes too quiet, and the microphone boost is off. The noise gate has never helped either. Oh well, I don't know. I don't know what it is. I don't know what it is. I've never been able to figure. Maybe it's just the microphone is messed up. I could try. I don't know if the webcam microphone is any good. Hmm. All right. Well, I'll try not to talk too much, and that won't be an issue. So, Bad Fly Dog. Here's the answer to your questions. Question 1: do you render text glyph by glyph? I'm not sure what you mean by that. What, as opposed to what? Rendering it like magically all at the same time? I'm not sure what you mean. And do you keep text as raw data, or do you split it into separate lines? Right now I keep it as one long array, and I've tried several experiments with different data structures and found that the most optimal thing I could do is switch to a gap buffer, which I'm going to do sometime this summer. But that doesn't really do it. That's not like a data structure per line or anything like that. It's just one big array with a gap in the middle and then another big array after that, and then the gap is wherever you want to insert characters right now, and then you move the gap around to accommodate, because normally edits are not like going from the beginning of the file to the end and all over the place. They're normally near each other, so moving the gap around is cheaper than always inserting and shifting everything afterwards, and it just turns out to be a really, really good system for text editing purposes. Yeah, I don't know. I'm not like I don't really have patience for things like sounds not working. I would love to get it to work, but I don't know how to even like troubleshoot that kind of stuff. I don't have a nah, I just don't have the patience to learn any of that. So maybe someday I'll get a microphone and that'll fix it. But anyway, we're gonna move on. So hopefully that answers your question, Bad Fly Dog, and you can tell me if you want to clarify in the first one what you mean by, like, I guess I do render glyph by glyph, but I'm not sure what you have in mind that's the alternative. Anyway, so don't have to do a subtract. Yes. So the thing is, right now, I'm going to run it, and we'll see that it's not working. Oh, wait a minute. Oh, it's not built. Right, right. I made a change and I haven't built it. So what happens here, and before I take this, let me take this back out actually, because I added that while I was chatting about how things work. But I'll show you how this works right now, just so I can get everyone caught up with where we are. We get caught in this loop. And the reason is that we should be at position 9, yes. We are now at a state where we're at 26. We want to transition to a new state. But the weird thing is that's a bug. 26 is the 0 submachine, which means it comes through here, it goes, oh, time to transition to a submachine, and then we find out what new submachine to go to, and it takes us back to 0. That should be wrong, right? That should take us to a new submachine, and then setting state to 0 would be fine. But if I set to state to 0 now, it's just going to continuously send me back to the first submachine over and over again, and I'm never going to actually, like, you know, advance at all. It's always going to, go back to the 0 submachine and interpret incorrectly whatever character it sees as if it was the beginning of a keyword instead of in the middle of a keyword. So I don't want to set the state to 0 yet until I understand why I'm getting state equals 26 right away. So my assumption is that the tables are just encoded wrong, although I don't know that for sure. So let's load this up. I want to fix that. I keep telling myself that I'm going to fix that, and I never seem to actually do it. So anyway, if I come down to the bottom of this page here, are we... Yeah, that was weird. It didn't use wrapped lines, which is unusual. Wonder if that has something to do with a change I made recently. Okay. Anyway, so okay, that's too far up. Here it is. So this is where we begin, and yeah, this just has a bunch of 26s encoded into it, but none of that should be the case. And I'm wondering if like the next one also just encodes everything as 26 and so on. Yeah, it looks like we don't actually have the code that figures out the correct way to transition to the next table, and so it's just freaking out and doing nonsense and putting in 26 instead. I'm getting more complaints about the sound. Is it actually worse than usual or not? If it's worse than usual, we can take time and try to find the source of the issue. Seems like it's an issue today, so let's give it some time. So let's see. Crackle, pop, sound, OBS. Let's see if it's an OBS thing that I can. Audio popping, crackling. Alright, so let's take a look at some things. So, settings, audio. Desktop audio device, default. disable. Let's try something here. Can you hear me? Can anybody hear me? Can you hear me? You can hear me? How does it sound? Does it sound better? Is this better? Awesome. So I finally think I found it. Which is kind of surprising. I mean, I don't have a way to mute myself on OBS anymore, but it's weird, like the little bar here doesn't show the red anymore, but is it like a lot better or just a little better? I'm curious. Blah 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 blah. Filling out some space here, but the red thing is gone, so I don't know how I mute myself anymore. But it still shows audio coming in. You guys say you can hear me, so that's weird. A lot better, huh? Well, I did the right thing finally, but I don't know why. I don't know how that's supposed to work if I don't. Maybe if I restarted the stream, it would be better. So there's a thing. You don't want the auxiliary thing, whatever auxiliary audio is on OBS. You don't want that feature to be on. You don't need that to be on. The other one doesn't let you pick which device to use, but apparently I had them both. I had them both on, and it was like somehow confusing it. I guess I could disable main and then run just through auxiliary. We'll run some experiments in the future, but for now I'm happy. If it's better, then we're good. So. Yes, this encodes 26s everywhere, and I believe that has something to do with just the way we're filling out those tables right now. So, this is up somewhere near the top now. If I look for keyword stuff, yeah, generate the keyword FSM. So let's read through what this does now, because the only thing I think that was left to do to get this to work is we need to learn about how this generator works again, and replace these 26s with the values that they actually need to be. And to be clear, the values they actually need to be are any value. By the way, why there's a lot of them? Is this just a lot of places where it needs? I guess there would be. It's got to transition to all of them at some point. Yeah. So anyway, all these 26s need to be replaced with a number greater than 26, but like less than like 57, I think, or 52, which represents the table we actually want to transition to at that time, right? So where does that happen? So we're filling stuff out. We process a match node. I think that's where things get interesting. We process a match node. As we're processing the match node, what happens? We read across a loop. We look at which words we still match. We get the SAF, which is the string and flag that we're trying to match. And then we take the SAF and we check the length of the SAF and we say, does this still, like, is this string still, are we indexing within this length of the string still? And if so, we say, here's the next character we care about. And we say, do we already have a transition rule for this character? If not, go ahead and get a new node so we can transition to this character. And at that node, set this set the index of this node there. Next index. What is next index? Okay, so next index is the index into the string we're checking, right? So we say the index of this node is however far into the string it needs to check, and let's see. Next node state, we get a new terminal state if we're doing a state override. And I forget why we do state override. Okay, we do state override because we're limiting the number of states. So we get a state override here because we use state override here because basically we're doing a transition to a different table, right? So this is right here where we're encoding a state. So FSM get term state. What do we can encode in there? We encode this override value, which should start at like 26 and grow from there, I believe. Or maybe it starts at 0 and grows from there, and then later we need to add that in. But where do we generate the table from? Also, where do we set the terminal states? If next index equals L exactly, then if the terminal table equals 0, and I believe it does, terminal, I don't think we're using a terminal table anymore. I could be wrong. We might be using a terminal table. I guess we must be using a terminal table because it says right there that state override gets set to state count. Pass that along. Yeah, it looks like we're using a terminal table. Okay, so the terminal table basically is a two-way lookup table from terminal states to the token type that that terminal state represents, and vice versa. And that means we have a state for, in our terminal table, we have a terminal state for like 0 and so on. We filled all those up, and then state count. You're telling me that we're using state override starting from hmm. It's a little weird because that means it's starting at state count every time. Does that mean that they all use state count? Because that seems wrong. Yeah, where does table transition and totally finished come from? Table transition starts at 26. It's just built right in. And ls key totally finished is final state. Right, where does final state get set? Final state is table transition state plus FSM stack dot count. Okay. Process match node. I'm not totally sure that what this is doing is right. So I kind of want to walk through it in a moment, but I'm going to read it one more time. So it gets the terminal table state count, which, as I understand, is the number of terminal states that we've set aside so far, and starts from there, and then assigns a number to each state as a terminal state right there, and then increments that number. And it does that for all of the possible matches, right? It can also, the other thing it could do is unjunkify, which I believe means, I'm not sure why we're asserting that it is less than 55 there. That's a bit odd, but yeah, I don't understand that. I feel like that's just old crusty nonsense. But the other part makes sense. So the idea is we have this terminal table, so we say type to state. We know what type we want to end on, so we get a state that is available, and we store that into the unjunkify here. And then if we got to the end and we want to unjunkify anything at all, we say, all right, this is a transition rule in this state here. Let's see, if the transition rule is equal to the terminal base. Okay, so the idea is that this is a node we're processing, which involves having looked at the next character of a bunch of strings, and if any of those strings wanted to terminate, does that work? Because what if there's strings of different length? I feel like I don't understand that, because there could be strings of two different lengths. Okay, so anything that, right, that makes sense. So anything that doesn't terminate now, right, will already have a new state value set up here, is the idea, right? We add the transition rule right there to be specific, right? We say, here's the new transition rule for this thing. So anything that didn't get a transition rule, it all terminates according to this termination rule here. And the reason they all terminate the same way is because they either have all matched so far, or they wait, if next L, or if anything doesn't match, like if we see a space, I'm not sure that I understand that totally either. I want to walk through that. Okay, and then how many levels are there to go? If there's just one level left, we go ahead and push a future FSM onto the stack, and we do that for every single sibling, like every single child that we haven't processed yet, right? Otherwise, what we do is we loop across all the children and we just process them, and then there you go. Okay, so the things I don't understand are, how does this actually do its job? It seems like that's just giving all of them the same terminal state, when you might have some that need to use like a positive terminal state that says, hey, I identified this string, while others say, hey, we found just wrong stuff, just the incorrect thing. Although I guess this somehow implies that, yeah, this is saying no matter what we see, it's correct. But I don't know if that's true or what the deal is there. Maybe it's something to do with how these things get initialized that I don't understand. It might have been initialized so that those don't have the friendly terminal state to begin with. It's just a different terminal state that those go to. We'll see. The other thing I don't get totally is why the state override happens the way it does. I feel like that is a bit weird, and that needs to be smarter so that it encodes inside the state which table it wants to transition to. Although maybe it doesn't know yet is a part of the issue. Right, because the table it wants to transition to will not have been generated yet. Because they get generated from left to right, so the future tables haven't come out yet, which would be a bit of an interesting issue, but you can kind of predict when it's going to come out and where it'll be in the table. Alright, we're going to walk through it now and see what we learn from that. So I want to walk through the table generator program, and I want to see basically starting from here, line 556. Okay, so I've got the wrong debugger up. That's for not the interesting one. I want a lot of stuff in this folder. I want the FSM Gen.exe, dev env FSM Gen.exe. Heyo, Fucon, how's it going? Welcome to the stream. Okay, so I just said this number, 556. That's where I want to stop. Nope. Perfect. Ah. Connor, what do you mean buffers showing through each other bug? I don't think I'm aware of it, unless you have a more specific. Maybe I'm aware of it if you explain how you trigger it, but I don't understand your description of the bug. I'm using the most recent 4coder. So you're talking about that? This thing where if you go to like just 0, it screws everything up? Because I'm aware of it. I've just been ignoring it because it's annoying. Basically that happens because the clip range becomes 0, so the OpenGL clip stuff doesn't work. And I haven't told it to just like not render when it's that small, which I could trivially do, but I'm lazy. Yeah. Okay. Yeah, I'll put that on my to-do list. It's just me being lazy. There's no reason to leave that this way. Okay. Da, da, do. Yeah, I was worried, Connor, I asked which one it was specifically because I was worried, like, in the past there have been similar bugs that were more important because they happened when you weren't, like, squeezing one view down to 0 pixels wide, right? And then it's like, that can't happen because now it doesn't work. Now you can't use it. Okay. So, I want to walk through this, but the problem was it wasn't built recently enough or something. So there we go. Let's see if that works better. There we go. So, I want to walk through and see everything that happens. Alright, so unjunkify starts to 0, state override starts to 0, terminal base starts to 26, which is fine. And levels to go is 2, so we don't do anything there. State count is 29, so it seems like state override shouldn't start with state count at all. I'm not sure what the deal is there. But okay. Anyway, yeah, maybe I was thinking that too. I need to. That's why I decided to get back to Lexer, and because Lexer is sort of like an optimization practice for me. Although it will kind of become a part of the project too. It's like kind of not necessary right now in any way, so it feels like practice to me. Is the big idea here. So next index is less than 4. Yes, that's fine. So we're gonna go ahead and process this, and this character won't have anything yet because it's the first time we're seeing any characters. So yeah, so T needs a new. This is for the true keyword. So we're going to go ahead and say, all right, this node needs to be created. We init the node. I'm curious what happens when we init the node. We say we might need to match 77 things. There's your max. That syntax would have to be changed someday. What's the next index? 0. Do we have state override? No. So let's see. So there we go. Whoops, wrong window. We get the state off of that node. So let's see. In there we basically just have, there's no override. The override just encodes, hey, if you transition to this state, this is a terminal state, so just use this, don't do anything else. And otherwise, you use all this information. Now, all of this is set to the terminal base to begin with, it looks like. So the whole thing is filled with terminal base, right? That whole thing is terminal base. Which, speaking of which, I'm curious to know, is anything in our current state, this state here, it's all 26s, right? It's all just 26. Yeah, that's what it looks like. So, we don't have a newest child yet, so we go ahead and say this is the first child of our node, and then newest child equals that one. We increase the count, we add a new word to the list, and we add a new transition to this state. Specifically, we say T needs to transition to, and then what's FSM index doing? It's figuring out, why is override a keyword in Visual Studio? Screw you. Okay, so result is you take the state that you're transitioning to and you figure out its index from the states thing. That gives you that. There's no override, so result just equals that result, which is 1 terminal base plus override. So override wants to start at 0 and increase from there is what it seems like. But instead it's always starting at 26. Okay, we're going to keep going because of the weirdness. I feel like that was just like filler, and that code is junk. Okay, so this keeps going for a while. And then finally, I want to see if we ever get to this state or not. Okay, so we didn't unjunkify this time, which is fine. When we do unjunkify, I want to catch it, because I don't totally understand what that does anymore. How many levels are there to go? There's 2, so we go across all of our children, and with each one of those children, we go down a level. So now we're at levels to go equals 1. We have a stack for unfinished FSMs. We have a terminal table. And let's see. So now levels to go does equal 1, so we go ahead and do that. And that sets state override to 29, which is weird, right? That doesn't really make sense. Okay. Is that where the 52s come from? That's 55. Okay. So the next index we're looking at is 1, and this is still a 4. We're looking at the true, I assume. How many words do we have? Just the 1? There's 9 words, okay. So you get C, which is R for true, and next nodes is not set yet, so we grab a new node, we initialize it, we set the index to 1 on this node. State override is true, so we give this, we get a new terminal state off of this terminal state stack, and then we set its override to 29, which should be 0. Which is weird, because if it has an override of 0, I guess it has an override of 1, because no one needs an override of 0, right? 0 is the first table which no one should ever transition back to. So, yeah, it looks like it's an override of 1. Is what that should be. And then this is the first child. We add a transition to this table here, and this time the override is true, so we do terminal base plus the override. We just put 55 in there. It's totally bogus, and so on. Okay, so we finally hit some point. It was 6 characters in. We hit some point where this is going to happen. So I want to see some stuff first. This state, what is the deal here, man? What are you up to? You're not an override state, because that wouldn't make any sense. And you're all 26s, which means you don't have a single real transition yet. And we have a terminal table, so we're going to set the unjunkify to whatever type comes out there, right? Which is what? Flags was 26. Type to state. Interesting. So that's just a 26, which is presumably where the 26s are coming from. So that just means, I guess, that yeah, it's a bit weird. Okay. Okay, so we have an unjunkify value now, which is 26, which means we're going to go through everywhere and see, hey, are you equal to 26, and then set you to 26 plus 26. Okay, that's where the 52s are coming from, right? Yeah. Okay. So that's just another load of bullshit. Doesn't make any sense at all. Yeah. So when we're unjunkifying, what this is supposed to do is say, look, if no matter what we see next, what I don't get is how this encodes, like if I see a the next character, if it's a space or a tab or a new line or like a non-alphanumeric, that's different than if it's alphanumeric, right? If it's like a parenthesis, that doesn't mess up the keyword. If it's an underscore, that does mess up the keyword, right? So that's not being handled in this system at all, which doesn't make any sense to me. I feel like I don't like half of this code here, and that what I actually want to do is scratch the process match node code and redo it. Now the problem with doing that is there's someone else who uses process match node, and they don't use all of the fancy features, and that's this guy here. And I believe that that one is working. At least last time we were able to test it, it was working. Because it doesn't use levels to go, and it doesn't use the terminal table, and it doesn't use the unfinished FSMs. It just uses the sort of plain vanilla version. So what I want to do is say, let's just save this. A lot of that code is nonsense, I think. I'm going to write a new one that's going to take in all of this stuff, but we're going to like redo portions of this to make more sense. Okay? Because I don't really understand what was going on with this, if I'm being honest. So I want to take out, let's see, I want to just bake in all of these values now, right? So instead of this, we're going to bake that in. So where is terminal table? Does levels go equal 1? No, it never does. What else doesn't build about this? 432. Terminal table equals 0? Yes, terminal table always equals 0. 445. Does levels to go equal 1? No, it never equals 1. 446. None of this happens. Okay, so this, I think, is the way it worked before I messed a bunch of stuff up. I think state override might also be totally not necessary. No, because that looks like that's just always going to be 0. So we'll always just get a new state that way. And there we go. Okay. So then this one will have this extra information and we'll handle it properly. So step 1, if we have one level to go, what we want to encode here is a thing that starts at 1 and then just perpetually increases as we go, because that will tell us which table, this is supposed to tell us which table we're meant to transition to. So when we encode whatever we put here, right, whatever we put here needs to be the correct table index, and the best I can think to hope is that that'll come out and we'll say we need a terminal state here. Still don't feel, it's just not quite right. How is it going to handle characters that are non-alphanumeric? It seems like the first thing we want is to distinguish between an alphanumeric and non-alphanumeric, and that's not happening anywhere as far as I can tell. We look at a character and we say we need a transition rule, and then we need a thing that says, alright, if this is the end, yeah, I'm not sure. Okay, we're gonna just assume that we can write all of this again from scratch, because I've had enough of thinking about this old code. Okay, so the idea is basically something like this. Each node or each state needs a full set of transition rules. If a character is seen which let's see, the most transitions should go into not a keyword state, right? So what I'm saying is most things will go to this, hey, this is not actually a keyword, we found something about it that's not a keyword. The exceptions are 1, when we see an alphanumeric character that is the next character of an actual keyword, when we have just seen an entire valid keyword and the next thing we see is not alphanumeric, or when we need to transition to a new table to continue. So that's specifically when we see an alphanumeric character that continues an actual keyword, and we need to transition to a new table to continue. So that's like actually more like subpoint, right? May need to transition to a new table at this point, right? Okay. And then what I want to do, I think I know what I want to do here. So here I process a node. And here I've got this thing called pop future FSM. I don't want that. What I want is more like I equals 0. Am I using I inside there too for something? Yeah, for comments. Okay, fine. I'll introduce a J, and then the J will be used for comments. Place I with J. Yes, yes, yes. No, no, yes. Done. Okay. So I equals 0, and then I want to get unfinished futures dot whatever I, basically, right? And really this can be a for loop, just like everything can be a for loop. And we'll just keep going while I is still less than the number of unfinished futures. So we're not going to pop things off of this anymore, is my point. Count. Futures. Okay. Whatever is futures, and then futures, is that a pointer? Yeah, so really I want plus I here, right? And so I get the next future, and the future I get is tied to a specific index, right? That way I can say I want to transition to a table with index blah, and put that on the futures to get to know which index will go with that. And I need to make sure that those match up all the way through. So the first FSM I gets index 0. Basically all the way through, what I want to know is, let's assert that my FSM minus the FSM stack dot, let's see, FSMs is equal to I. That way I can say that I know for sure that the index that I'm using to specify the future FSM is also the index that that FSM ends up getting, so that the indexes will line up like they're supposed to. And I think there's going to be an off by 1 there, but I'm going to leave it and deal with that when I can see the evidence for sure of exact. Because off by 1's too hard to think them through. Just look at how they line up and adjust from there. So then what will happen is let's see, we allocate a new FSM, a new tree, we initialize them, we grab a root state and a root node. That's fine. We copy a init node, match copy init node. What does this do? Future source, match copy init node. Okay, so we copy the root node from the futures source node. That way the root node is a copy of the node we had before, right? Because the tree basically, we can just look at that node and go, give me all the content of that node that we want to look at. And what exactly happens there? I'm curious. I think that that's just mainly copying which words we still match, right? So yeah, we're grabbing a count there, we grab malloc, all that, and then we mem copy. Sure. Why don't we just use the same array though? Yeah, I'll just leave it, but not really a memory usage concern in this one. Okay, we write out a comment, and then we process the match node. And the way that works is we say don't go more than 12 steps, because we determined that was a good number for this. We say here's where to get, if you need a future table, go ahead and put it on this thing and get your index out. If you need a terminal table, here it is, and so on. So this will be in charge of getting that override index correct now. And okay, so that seems like a slightly better approach. And now let's go ahead and say, I'm going to peek at this and say, what is the first thing this kind of process does? We're going to do a loop across the match count. And where does the match count come out from? The match count comes out from the node. Okay. So, the node comes in right there. Okay. So we have, let me put this, whoops, right here. Node match count, and then we're going to do I equals 0, I is less than match count. We're going to look at each of the matches again, and we're going to say if any of those matches yeah, so we need like word index, which is we look at the words and we index out that. So now words is a thing and word index is a thing. And word index comes from the, or words comes from the node as well, I believe. Yes. So now we look at each word from the node, and we get the word index, and then we can look up the string and flag, so the saf, like so. And the saf is just what you get when you go to input word index, right? Okay. So now we have the saf for that word, and that is enough for us to go and get the length, right, out of the string. So we're going to need a length up here. Okay. So now that we have the length of the string, what we can do is say, okay, what is the next index? And does index get passed in here? Where does next index get computed? I can't. I guess that is in the node, right? So we have next index equals node index, right? Is that the basic plan? Plus 1. Wait, that doesn't make any sense. Oh, is the first one -1? That makes sense, actually. Okay. So yeah, I'm guessing that first node that comes in has a -1, so we get a 0. Which is where we want to start. Okay. So then, what we can do is say, look, if the next index is actually less than the length, right, then we can still index this string. There shouldn't be two strings that have that are like, when we check, like there shouldn't be two strings that have matched all the way up to character K, right? So there's characters 1 through K, and they all the characters have matched, and then they both end at the same time. That means we have two strings that are the same. So that should never happen, right? So this needs to be like assert that this path hasn't happened before. So else if next index exactly equals the length, which if it's not less than the length or exactly equal to the length, it's not entirely clear why it would even show up in this node either. I feel like that I want to just assert that that is true for now. And then assert that something like good transition equals false, or equals 0, or whatever. And then set good transition equal to, this is where we take the terminal table, and we go from type to state, and we get what do we get? We go from type to state, and we use the SAFS flags right here. Right, because that tells us what type in this case. The flags are just mean type. And then good transition should be non-zero, and we shouldn't see another good transition in this batch. And in addition to that, we also want to say add in whatever certain amount that will identify this as we'll have like a real transitions or real terminate base, right? And that'll just be like, look, real terminate base is like 65536, so that it'll 65536, so it'll fit inside of an int and blow out anything that'll fit inside of a character by a lot. And then when we go to encode this into the final FSM table, when we go to actually write this out, we can finally do the last minute adjustment of saying, oh, this is in the real terminal state, and then pulling that out and turning it into the correct, like using the correct base, because we don't know that the trick is we don't know the correct base for these values now. So I'm just putting in a large base, and then we'll detect that that base is too big and rebase it. So I see an interesting question. You'll have to excuse me, I don't know if I'm going to pronounce this, but something like Jose Marriott or something like this, Marriott. I don't understand why this Lexer needs to be a full-blown abstract FSM. Why not just write a standard Lexer and snapshot the current offset token within the file? I'm not sure what you mean by snapshot the current offset token within the file. But the reason, and it doesn't need to be a full-blown abstract FSM. I want it to be a full-blown abstract FSM because it's fun to do. But the reason I find it fun, to give a little more meat to that answer, is because it lets the Lexer be completely resumable. So it's not building an abstract syntax tree, it's just getting tokens, but it's fully resumable, which means I don't need to stringify the entire file to lex it, right? So if you imagine the way normal Lexer works, it is actually like if you just do ifs and like, oh, check the next few characters, blah, 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 it gets to be difficult to lex. Say if I gave you, like, the whole thing was in 1 kilobyte chunks, and I didn't want to take the time to concatenate them into one big string, it would be kind of hard to write a standard Lexer that way. Boiling everything down into you put one character in and then a transition state, and you put one character in and a transition state makes it very, very easy to build one that works by just arbitrary chunks that are broken up that can be broken at token boundaries without causing problems. And that's the real goal that I set out with. And now what I'm doing is overkill. It works. What I was doing was just as I'm going, I have a backing buffer that stores the current token, which maybe that's what you mean by snapshot the current token. I had a thing that would, as you're going, it would say, okay, here's the end of a token, we can throw away the back buffer. So that way you could do chunks, and it would use this backing buffer to put a whole token together for the case that if it's a keyword, it needs to be able to identify which keyword it is, and so it can't be broken up across two boundaries where you can't get back to the old text. And that's fine, but if I get that out of the main loop, it'll speed the main loop up. That's the backing buffer is the number one, like, blemish in the design right now, and so I'm trying to handle keywords across boundaries without having to look at the key at the beginning of the keyword by the time you've finished reading it, right? Which is what is a little bit tricky now. Oh yeah, Volbus is asking if I solved the memory problem that I was talking about like yesterday or sometime earlier this week. And the answer is yes. What actually was happening was pretty interesting. So I have this undo system, and it turned out to be originally I built like this thing. It was like an undo stack, and I only intended for there to be like 2 of them. But then as I worked on it, there ended up being 4, and I was like, eh. And I'd really like to get that down to 1, to be honest. And maybe that's possible, but it might be 2 if I keep the history system, because the history system is kind of cool. If it's a bit unclear to me if I want to keep the history system or not. It has some benefits, but really it's only helped me like twice. The undo has been the thing I use most, and the history, not as much. And so I'm not sure. If I got rid of the history system, I could get rid of one of those stacks. But the bug was that it involves a combination of a lot of different nasty things. So there's a thing called a batch edit, which allows me to group multiple edits into one bigger edit that I can undo and redo all at once. And doing batch edits has some other advantages, but from the undo system, that's what it does. So basically what that involves is I have one of the undo arrays is for children of other undos, right? So if I have some undo or redo or history undo redo that needs to be encoded as a batch edit, then what it does is it says, hey, I have children. Here's the first child that I have, and that's an index into the children array, and then the stuff in the children array just sits there forever, right? That's the basic plan, and it seems like if you're going to have stuff that just sits there forever, you could boil it all down into one big system anyway, so that's what I want to do in the future. But, so you got this index to the child thing, right? And the thing is that means some of the normal data, the stuff that encodes a normal edit inside that struct, is still there, it's just nonsense. I don't know if it's uninitialized. I think it's actually like the number, like the size of the edit that is written into that is the same as it's either the number of children or it's the size of the first edit in the array. I think it's the size of the first edit in the array. But it's just like, it doesn't actually encode the information you care about at all, and when you undo that, it shouldn't affect the real undo stacks like string stack, because you didn't actually encode any of the undo information into the undo stack. You encode it into the children stack. And so when you do the undo, normally what happens is it backs up based on however large it thinks the string was on that stack. But that value was garbage, and I was not checking that correctly. What I should have done, what I switched to doing, was saying, if there's a child on this, then don't update the undo stack. Only update if this is a normal edit, a single edit where the undo information is encoded in the undo stack. But anyways, what was happening was I was basically backing up the stack pointer below the beginning of the stack, and therefore I was like, my pointer was looking at one of the other undo stacks, or depending on how they ended up getting laid out, it might be looking at one of like the metadata stat arrays for the buffer itself, and then you would do like a delete, and so when you do a delete, it has to store whatever you deleted, but it's now storing it at a negative index into the array, which means it's overwriting some other buffer, or potentially the metadata that you don't want it to overwrite. So yeah, that was the corruption bug. Took me a long time to track that down. But the lesson that I learned from that was that the hairy undo system was too complicated, because I was walking through it, figuring things out, and I was like, oh man, this is too many layers for me to figure out what went wrong. Like I see what went wrong at this end, but I don't know what, like I still know, like I know 90% of what happened. I didn't ever actually find where the source data came from specifically. Like it's too separated, so I wasn't able to reproduce it in such a way that I caught it when it was produced. I can only catch it like once it was like about 10% of the way through the process. So that's not a good sign, and I felt like I needed to redo the thing. So that there are just less layers of passing this from the thing that produced it back to the storing it and then it's just got to be simpler. So that was what happened there. Anyway, so the idea here is we get this good transition, and then when we're done, if we have a good transition, then anything is we've just seen an entire valid keyword, and if we saw a non-alphanumeric, right? So what we want to do is say, maybe that's what this actually does. This goes across everything, and if the so this is somewhat broken. And I'm not sure how. Maybe the preprocessor doesn't actually work, and I should double check that. But what we should actually do is go across everything, and say, if char is alpha. Do I have like an is alphanumeric? Okay, we're gonna do it. Char is alphanumeric. Char I. Right. So if I'm looking at an alphanumeric character, whoops. Then what I want to do is, and technically, if I'm not looking at an alphanumeric character, then what I want to do is I want to transition. I don't really care about that. I want to transition to the good transition there, right? So anything that should end that word will transition to that. That's what makes sense to me. And I believe that the states maybe encode their transition rules as characters right now. Let's just go ahead and make those ints so that I can, I like those unsigned ints so that I can truncate them later like I'm planning. Alright, so that caused some issues. Alright, 175. Let's just count. Okay, 491, 498. We don't have an I. .503. When 503, it's a warning. Conversion from size T to int. I'm okay with that. 508. Assert that good transition equals 0. You are right, I haven't assigned that or declared that yet. So there we go, we have a good transition. 516. Alright, so we need char is alphanumeric. If x is greater than or equal to 0 and x is less than or equal to 9, or if x is greater than or equal to a and x is less than or equal to z, or x is greater than or equal to little a and x is less than or equal to little z, or if x equals the underscore. Result equals 1. There we go. .529. This state transition rule undeclared identifier. This state. Yes. How did I define this state before? So that's just the state from this node. Gotcha. FSM state. This state is just this node's state. Okay. 1306. Right, so when I'm generating from there, I'm looking at each of these, and what I want to say is, let's set this to an unsigned int. Let's have you cast down to unsigned char. And then what we'll do is we'll say if new state is greater than terminal, what is it? I forget what I called it. Base. Real terminal base. Else. Then I want the new state to be whatever I get when I take that, subtract the real terminal base, and then add in the FSM's terminal base. Great. Now what I don't know is why that actually exists already. It's a little surprising. FSM terminal base. FSM equals the terminal. What? So I'm passing... That's some crazy nonsense, don't you think? The terminal base comes from the FSM and then gets assigned. I guess I just switched to passing that through the FSM. So when I process a match node, does this FSM know what its terminal base is going in? FSM init. Ah, so the terminal base does get set right there. Okay. Generate FSM table. I think I want to say unsigned char real term base goes here. I don't think that that's the same terminal base. That's the local terminal base, not the wait, what is this? Yeah, that's not what I want. Generate table from app. There we go. Okay, so real term base, and then we'll add in this real term base. There we go. Connor rent? I don't think so. I don't sell these hats. If you'd like to buy one of them, I guess I can sell you one. It'll take a while for me to get one made. I don't have a huge problem with it. Or I mean, I guess I don't have any problem with it. Just wasn't planning to sell them, but we could work something out if that's what you're thinking. Okay, so yeah, I want to generate table from abstract FSM. Connor, I'm not sure. I'll go check how much this one costs. I forget now. Oh my goodness, Mibble, there's a hat alias in the Insobot. That's awesome. Way to go. Alright, so yeah, the preprocessor directive tables look like they just worked, so I don't need to assign them a real terminal base. But the part terminal base, unsigned render, what is that? Tables. If I come up here, do these really have a terminal base rendered with them? EQ, I don't see. Okay, so where is part terminal base. Okay. Yeah, we don't need to render that because that's coming out as this define down here. So that's fine. Alright, so, the issue I'm dealing with now is we've got this, so, final state, right? Keyword FSM's the final state is the base that I want to rebase everything to in there. So that's better. Not sure what it just generated. Also not sure why it always does that. That's really annoying me. Also not sure why it always loses the information about the buffer when I do a reopen. Alright, so what's going on here? Alright, so it's just not generating any tables right now. Or it's like generating an empty table right there. That's bad. Bad news. Yeah, that table looks like it's working, so it's just this one here is all messed up. Right, it's got table 0 has an EQ class, it's got just the one EQ class, and then it just transitions to itself and calls itself a day. Alright. But that's alright. I'm not finished. I am not through with you yet. Process match node. Boom. Boom. There we go. So it's now all set to blah 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 blah. We just need some of that stuff from process match node that was not so bad. Specifically this for loop here that continues on. We want that, and we also want the version that's a little more complicated with the levels to go. So if levels to go equals 1, we are going to have one behavior, otherwise we're going to have the normal behavior. And the other behavior is actually, I think this will just be not here. We're going to push the futures on immediately instead of putting them off. As soon as we know that we're going to need a future, we're going to put it on the table. And then, yeah, that seems good. And so, what that lets us do is say, okay, when we're right here, I want char C, I want C to equal the SAF strings next index, right? And then what I want to do is say, how did I do this up here? I have like an array of pointers, I assume, next nodes, newest child. That'll looks good. So let's grab some of that stuff. That can go right here. So let's memset real quick the next nodes to 0. And it goes like this. If the next node's C is 0, then blah 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 blah, else blah blah blah. Okay. And I think that some of that other stuff related to that was messed up. But I'm going to grab a copy of it because I don't remember all the init code. So we're just going to grab this and see how close it is to what we need. Looks like we don't need an else case. Alright, so let's see. This is the part I don't remember. We get a new node off the tree. That looks fine. We init the new node. That's fine. We set the next index to the index of that node. That's fine. We get the FSM get state. So we get a new state for this finite state machine. That's fine. So the thing is right here, actually, right? When we're building this new node, if I'm going to assign a new state to that finite state machine, I have to assign it a terminal state right there if we're on level 1. So this is where it's going to change up from before. This is going to go if levels to go equals 1, one case, else blah, the original case, right? So then it's just a matter of next node's C state equals FSM get state, FSM, or get term state, FSM term state override, right? State override. Override. There we go. Here's a name that exists. And so that needs to exist right here, and there we go. And so override will happen when we get a new, we're not using this function, push, there it is. So I want that to now return to me the index that we get. So index is the stack's count, which gets incremented. And that goes right there, and then we can return that out the other end, right? So I push an FSM on, I get the index off, I get a new future pointer, and I set the future source to this node that I asked it to use, and then it tells me the index of that future, which is going to be useful because that index will let me associate this correctly down here. So process match node, I get the override somewhere here. This process match node, I mean, I get an override, and I want that to be equal to the push future FSM onto the unfinished FSM's stack, and give it the node that we're looking at right now, right? So we say, hey, we're not actually going to make a new child here, or we're not going to associate a real state to this system and process it. What we're going to do is push a future FSM onto the future stack, and whatever index that one lines up with, that will be the override for this, right? And then later we can take the overrides and add them to the base for that section of the state. And that should be good. So we grab the override, we push that on the term state stack, we store that as the state, and then down here we have this question of who's the newest child. If it's nobody, then hopefully we don't have a first child yet, and we set the first child to this one we just created. Otherwise, we let's see, what is this doing? Otherwise, we set a next sibling onto the current newest child. We update the newest child. What does count do? Nothing. It looks like we were just keeping a count maybe for debug purposes at some point and never took it out. So that's gone. And then finally, let's see, so we're saying count doesn't get used up here, so I'll take that out too. I have this feeling that what I should actually do is like redo this now that I understand how to make it all work. I should redo all of them with just like a better, like more careful design from top to the bottom. I think I've said that before too. It's just something I'm gonna have to keep around and maintain for a while. I don't want it to be so hacky all the time. There we go. So we add a new word to next nodes, and that new word is a word index now, right? Which means basically we're saying, hey, node, you actually match this word here. So there you go. That's good. and if we happen to have two different words that both look the same up to this point, then that node will match both of those words, because we won't do any, when we do next node C, we'll get the already existing state, and that way both of those words will transition to the same table or to the same next state within this table as necessary. Then we add a transition within this state for this character, with FSM index being okay, what is FSM index doing there? So it says, okay, so we assumed first of all that state might just be within the normal states and we set it. However, if it's not, then we have set an override in it, and then the result is just going to be the terminal base of this FSM, which is correct, plus the override. So that looks right. That looks right. 529. What is bothering you? Conversion from int to unsigned char. These are good points that you're making. That should be an unsigned int. And FSM get term state should use an unsigned int for its override. Actually, I take that back. We should make this the unsigned char, and that thing that returns int should return an unsigned char. And we should assert that the count is less than, or actually that the max is less than, well, how do we even encode the max, actually? Let's go look at that real quick. Okay, that is an int, so that should be less than 256. 284. Unsigned char. 566. Right, so that is like another node pointer. Match node n. Uh-oh. So tree count was not less than tree max the whole time. That's bad news. I wonder how that happened. So that was in here. Okay, so that's where it asserts, is right there. It's doing more than the number of layers it should do. And of course it is, because I'm dumb. Okay. Called the wrong function down here. So this one needs to call all of this. So it uses the same terminal table, uses the same unfinished FSMs, but it levels to go is one less. Man, still something's wrong. Okay. Alright, something's still wrong. So, boom. What's going wrong here? Still breaking really soon. What's it breaking on? It's breaking on count less than max. Ah, max is too big. So where did we set that max to be so big? That max can't be that big. We can't have 1,024 states. We can't have 1,024 nodes. Wait, how are we even? Okay, we're not. We're okay. So where did I set that? Right here. Right. So that's just bogus, right? I can't have this many. I can't. Yeah, I can't have that many nodes or states. I'm gonna set those both to 255. 606, 601. Now what? Come on. Ah, get out of here. Are these guys also too big? What's going on here? No. Tree stack 255. So the stack has a max of 124. I'm processing match nodes on recursively, right? This is okay. It's still the original one. Going in to process the match nodes. The tree has a max of 200. So what unfinished FSMs? Is that the one that's got? Yeah, that's the one that's got much stuff. And why are we saying the number of unfinished FSMs has to be less than 256 now? Oh, it does because each one... Okay, that's fair enough. Alright, so this one also needs to be 255. Okay. Okay, what's going wrong here? So we come in here, we're generating these keywords, and now we're asserting... Oh, okay, so this is after we got through here. Right, I expected this might go wrong. So the FSM we got... Well, what is I? I is 0. And what is FSM minus FSM stack dot FSMs? 1. Okay. So that means there's one thing on the FSM stack which didn't show up on the future stack. And I think that's because there's this first one up here that doesn't actually ever happen for real. And I'm wondering if that can't just be... There's the unfinished... Then we grab an FSM, we do all this work. Why can't we just say... The only thing that's different here, actually, is we do on the first one tell it to only go 2 steps instead of 12. So maybe we don't want that to be the same exact code path. But, and we also don't put a comment on it, so it's a little different, but that and that are the same. This is different. Okay, so these are sufficiently different that I shouldn't try to merge them. But what I still want to do is put a future on the stack to represent that, even if it doesn't actually get used ever. So what we'll do is we'll say that the for loop here begins at I equals 1, and right away I'm just going to push something onto the stack. So push future FSM onto the unfinished futures stack, push this root node here. There we go. So now we've got this. Let's screw everything up. Boom, there we go. And then pull back my generator. There we go. And then if I go down to the bottom, alright, I'm now generating all of the tables again. It looks like that isn't so bad, but it's still all going to 26. Why would it go to 26? What does that mean, that it's deciding 26? Something's wrong with the logic there for sure. Yeah, so all of this stuff still looks perfectly reasonable when I look at like the parts. It's like it's pairing things up by by sets of two characters that match, and um, and that's good. Blah, 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 blah. But I don't know what all these 26s are supposed to mean. That would just mean going back to the original table, which isn't supposed to happen. I assume that this right here is like the exit state, because I see that in a few places where it's like, oh, transition top right corner is some big number. So that's like, oh, we've concluded this is equal to switch or whatever, right? And in this case, it's like got a few of these, I bet. It's got 100 there, 98, 99. That's 3 of them. 102. Yeah, so it's got different states that all seem to put it in the right exit spot, which is good. And then it's got internal states here that do a good job of figuring out, like, it looks like maybe it's grouped the 3 A's together as one, and then there's one other one, so 1 and 2 represent the 2 things that might happen there, and then depending on which way you go, you end up in one of these 2 spots or something, right? And then these all go to the T, so that's the 1AT, and that's 3IC, right? Underscore, and then finally that's where things start to get a little different. There starts to be divergence between the behaviors there. Here you can either get the underscore or you terminate. Martin Cohen, I'm just using the hack font right now, so it's probably why you like it better. Still using STV true type though. The this one is one I think most people don't think looks very good. But now that the indent works better with monospace, I prefer having monospace again. Just the indent works better with it. Once the non-monospace indent works again, or once it eventually does, it never has in the past, but once it does eventually, then it will be different. Yeah, so this looks like it's encoded the right idea. It's just the 26 isn't the right fail terminal state, and I think that the reason it's doing that is that we initialize to that value, but there's some confusion within an FSM. Yeah, it's not a great font in general. The Sans Liberation, I believe is what it's called. Liberation Sans. Liberation Mono even looks better than that, but Liberation Sans is actually not very. It's like a shitty Arial. Anyway, let's say that I want. I want to separate out these concepts because it looks to me like the problem. This process match node is coming through here and it's saying, well, where is it? Where does it initialize? Push, yeah, so where do we do FSM get state? That's important. Right here, it's using the terminal base, which is the terminal base as stored by the FSM. But I think I want my FSMs now to store 2 concepts, not just the terminal base, because I have 2 different bases. So there's terminal base, we'll call this transition base. Transition base, right? And now I want to see all the spots where I use terminal base. So I'm going to actually comment that out and go through the errors, and some of them are going to become the terminal base, or the transitional base. So, for one thing, oh, but I don't know the real terminal base right away either. Okay, so I have to back up. So there's a few things here that are annoying, right? And this is why I wish I was using a system that I started from the ground up, because there's just some things that are a little hacky here. So here in process match node, we use terminal base, and the way we use it is we say that we take this and we are adding, yeah, so where is the real terminate base? Is right there. Ah, okay, so when I might come up with a good transition, I'm taking that plus real okay, I'm adding good transition to it. Okay, so the problem is when I go and decode that, I have a real terminal base, but I also need like so generate table from abstract So yeah, well, the final state should be correct. What's the final state coming out as now? 75. So I should be getting 75 plus all that stuff, I would think. Let me walk through this. Where's my breakpoints gone? Okay, there we go. So, terminal table, or not terminal table, this state, is it already filled up with 26s? Yeah, it is. So that's really weird. Where does that happen? That must be happening before this breakpoint even happens. So, root node match init node root state equals there. Yeah, so we come in here and it just fills the, okay, so that's the problem. It's when I'm getting a state, I have this thing called terminal base, and that is where it's crossing wires, because that terminal base is not actually the terminal base of this finite state machine. That's the transitional base. And I want to just spam the real transition base number everywhere. So FSM get state is going to just be parameterized on that for now. I'm going to rewrite this whole generator. And then what I'll do is I'll have another copy that I provide to myself that is just right, and then we don't need that. Okay, and then wherever I do FSM get state, which is down here, I can start by giving it the real terminate base as root state as a starting point. And same thing about up here when I'm doing get state. If I'm getting a term state, it's different. I don't care anyway. But this one, I want to fill it up with the terminate base to begin with. 540. Truncation from int to unsigned char. Okay. $625. Not on this buffer, stupid. On this buffer. Boom. Boom. So now that should be filled with, okay, it's filled with zeros, which is because we're truncating it. And that's awesome. Okay, so let's undo those unsigned chars and FSM get state unsigned int. There we go. Now let's see if when I run it, I'm finally getting, there we go. So now that's all full with all that stuff. And later when it rebases, it should rebase the way I would expect, I think, so that those will all be, I don't know what they'll be yet. Well, we'll find out. They should be 75 or something like that, right? So let's look at the tables again. Let's reopen this file, and then undo all the bugs that triggers. There we go. Go to the bottom. There we go. That is what it's supposed to look like. So all those 75s mean, hey, this isn't actually a thing. This isn't, I thought it was a thing, but it's not a thing at all. Right, now I'm guessing all these zeros here are maybe wrong. Well, I don't know. It's a pretty long line of code. Okay, so there's some stuff in there that makes sense. There's what happens on various alphanumeric transitions and things. Okay. So, now if I look around, there should be like a 76 somewhere in one of these tables. Yeah. So right there, that is the first word that completed. It was like, aha, here's a word that's completed, and it assigns 76 to that particular word. So false, right? So false gets the word 76. Martin Cohen asks, how do you generate the tables? It's a long process. It's been building up for, as you mentioned, a while. At this point, there's a number of stages, and it's the highest level stage of this part that's getting kind of hacky. The first stage was I wrote like the general lexer, right? If I go to like generate one of the less crazy ones, so there's generate. Here's the good one, right? Generate FSM table, right? So this is all it does to generate a table, is it allocates space for a table, which is just, you know, we tell it how many states it's going to need, and so it knows how much space it needs, and it generates from that. It can allocate the equivalence class table and the transition table that it needs, and then we set up a little finite state machine struct, which is just a little bit of information. It's a little bit overcomplicated, really. It could just be boiled down, but it is what it is. And so you got this struct here, and really all that is for is so that you can store a couple of ints. In the actual program, having it as a struct is more useful, but I was just copying code over from that, right? So really it's just like a pair of ints that are useful, state and emit token. And what happens is we pass in to a function called main FSM. So when I first wrote the code, I wrote main FSM, and it's really just a switch that implements a finite state machine. So it looks at the current character, And really there's one finite state machine per preprocessor state. So there's a few preprocessor states, and each one has a slightly different set of rules about like what can happen during that state, like the, you know, the whatever, right? I can't remember off the top of my head. There's like certain operators don't exist uh, in the preprocessor or something like this. I can't remember exactly what the difference is. I could look real quick. There's like, for instance, if we have an error, the behavior is that everything is the same unless it's a new character. Oh yeah, it's include, right? If you're using include, then the less than greater than things just behave differently as tokens. There is the idea. That's the main one, and I think there's maybe one other one that's important. Oh yeah, the pound operators. That's right. That's the other one. But anyway, the point is, what this thing is doing is really just think of this as some number that is constantly the same throughout the entire system. So we're generating one table per preprocessor state. And then we put in each possible character to generate the table. And we say, so first of all, I wrote this so that I like tested to make sure that the function was correct as it like with this being the finite state machine, no lookup table. Then to generate the table, I just in a loop go through all the characters, pass it into the finite state machine, and say, hey, finite state machine, what state do you transition to when you're in this particular state and this character comes in? And then it tells me, oh, I transition to this state, right? And so it tells me if it emits a token or not, and it tells me what state it transitions to. And then I just make a table that goes, all right, given that information, store like, okay, for this particular state and this character, store this, and then look at the next character, store this, look at the next character, store this. Right? That just becomes an array. Then I have a thing that like allows me to do things like flipping it and stuff, because sometimes as I was playing with optimizations, maybe it becomes more useful to change the order of operations so that you actually go, which character are we looking at first, and then like the major index is which character, and then the minor index is which state, or the other way around, so I can flip the table as needed, and then I have a function that just prints the whole table. And then the other thing the table has is equivalence classes. So to build on top of that, instead of having a huge table that's each character, each state, it'd be like 256 times however many states you have. It'd be a huge table, wouldn't fit in cache. And have these equivalence classes, and what the equivalence class does is it says all of these characters operate the same way, right? So you can see all of these things that are 0, that's because all of these characters all operate the same way. So they all have equivalence class 0, right? And the way that is generated is I just look across the uncompressed version of the table, and I mem compare each state, or no, each character, right? I go, A and B, are they equal? If so, I merge them into one row, basically, right? And I just compare, I find the equivalence class, I say, all of these things are equal, all of these things are equal, and so each one gets assigned an equivalence class, and then I have this equivalence class array come out of that, right? And that all gets stored in that FSM struct. And there's a bunch of different things called an FSM, so it's not great, but yeah, the FSM table struct stores all that information, and then I have a function that just renders that as the text that we need for that particular FSM. Then on top of that, what I've done is said for keywords, what I want to be able to do is pass in the list of keywords, and then I'm generating a tree that sort of is the tree that descends all the possible keywords, and then I'm like writing I'm procedurally generating the finite state machine code from that list of strings. So that's the harder part that I think is hacky. The basic part that's just like, if you have a rule that says state character, get a new state, that whole thing is pretty solid. It's the part that says, here's a list of strings, generate the rule, and then generate the table. The higher level step is a little hacky. That's the part I feel not so great about. That I'm working, and that's what I'm working on right now. And the other thing that I had to do there is I'm breaking it up into a bunch of smaller finite state machines, because one big finite state machine, even with equivalence classes, keywords is just too many states, right? So what I'm actually doing is saying process a few characters in whatever keyword you're looking at, and that's one finite state machine, and then use another step finite state machine But after that, you've differentiated it from like all possible keywords to like it's got to be one of these three, and then your finite state machine for differentiating which of those three it is just this one, right? So the keyword parsing actually costs the most memory, and if I didn't insist on having it, it wouldn't actually take up that much memory. As it is, it takes up a lot of memory, and I have some ideas on what I'm going to have to do to compress this. Obviously, I can't do too much because I'll give up the speed, which is the whole point of doing it this way, but I feel like the EQ classes can be compressed here because they're short. You have to make sure you don't like go with bytes and then I need indexes bigger than that. But I don't think any of these are exceeding the limit of a byte, so I bet I could switch these to bytes, and then I just got to come up with a way to deal with the fact that some of the tables will need shorts and some of them won't. Will use bytes, and that sounds a little tricky and interesting. Like I'll have two branches or something. I don't know, one for each. But yeah, you sounds like you got the basic idea. It's been a fun project. Okay, so what does that table look like right now? We said that looks good. What happens if I try to run the actual Lexer now? Ah, everything's wrong. Awesome. So it's terminating now, and it's all just wrong. And then what's it doing now? Is it looping on something different? State 46. I'm not setting state to 0 down here. That could have something to do with it. 507. Whoops, wrong layout. There we go. New Lexer. Interesting. So the state is 0. What is the EQ class? Oh, the EQ class pointer is bogus. What's the submachine? 49. So the state is 0. How did the submachine become 49? Position and position. Okay, so we're out of characters, which is the reason we've terminated, but the state, so we're going to set the submachine, and then we're going to set the state to 0. Oh, that's a problem. So I don't want to do this branch if I'm totally finished. Alright, so everything's broken, which is fine. That's what you expect at this stage. But I'd just like to see. So we're not emitting the tokens we're supposed to emit. Oh, there's still this to do down here. So we're not converting from the output state back to the actual token type yet. And, wait a minute. 202. Yeah, okay, so this is too long. I don't want to see all that. Let's switch to... We're passing a couple tests still. That's interesting. So it's probably just any test where there's a keyword, but there's also size mismatches, which is weird. Anyway, what I want is, I want to go over here, and I want to see if we can go to the experiment code finally, and switch this over to troubleshooting mode. So I want one repeat. I want verbose level as high as possible. And chunk start, I want no chunking right now. Single item, yes. Please test, what was it that was failing? There was a bunch of them. I want to do speed test. Who else is failing? Parser test 1. Is parser test 1 working? Experiment. Okay, so there's one for me to fix. I'm only outputting 5 tokens, which is weird. Looks like somehow the system gets messed up as soon as it sees a keyword, maybe. So, I think I'm going to call that a day. We're getting about within an hour of Handmade Hero at this point, and I don't see any reason in pushing it any more than that, and that's good. It's a good bit of progress. I feel like the keyword generator, the keyword finite state thing is finally starting to come into place. And I want to call it off before we get too much past 2 hours. I'll hang out a bit and see if anyone wants to shoot a last-minute question at me, and if not, I will sign off. You want to see if I switch back to Popcorn? You want me to try to run it without the new keyword stuff? I'm not sure what you mean the keyword thing. I'm not sure if you're talking to me either. Maybe you're talking to Miblo. Thank you, Josie and Marriott, or, however close I can get to it. Always good to have someone new on the stream. I think that's it. I don't see any questions, so I'll see you guys around. Bye.